All right, everyone. Welcome to the Introduction to Crystalon workshop. Hopefully this is helpful for some of you. This is going to be a pretty basic overview of the tools, but hopefully it's helpful, and I'll be doing more webinars in the future. I've got a list of links here, and you can download this PDF presentation. I think it's a button on the top right corner of the presentation. There should be something that says Shared Files. So you can download this PDF. I've got a bunch of links here where you can download Crystalon. We have a forum where you can ask questions, start discussions. I have the source files on GitHub, and always feel free to email me with questions or anything at info@f=f.com. Also, if you like Crystalon, you like this webinar, and you want to buy me a beer, you can donate. So today, part one is just going to be me going over a bunch of slides and boring you mostly with theory and applications. What is Crystalon? What's a lattice structure? Why do we use them? How do I make one? And then the last part, I'll do about an hour of a demo. I extended to make this 2 hours instead, just so I don't run out of time. And hopefully, if I go quickly, we'll have some time to do some questions and answers at the end. So a little about myself. My name is Aaron Porterfield. I'm an industrial designer from San Francisco. I've been working with additive manufacturing for something like 8 years, probably more. That said, I'm an industrial designer. I'm not a software developer. I'm not an engineer. I made Crystalon because it was just a set of tools I needed to make basically to do my own work. And then I decided to make them open source. So what is Crystalon? It's an open source toolkit for creating lattice structures. It's not necessarily a plugin. It's really just a cluster of native Grasshopper components. And I'll show you what that means later. And basically, I made it open source so that hopefully it's useful to people, but also hopefully that I can build a community and people can add to it and develop it further for all kinds of different applications, because I don't know how to do everything. Hopefully others do, and they can help out. And basically, it's modular. I made it as modular as possible to work together with other plugins. So the workflow is kind of broken down into smaller chunks so that you can use other plugins during the workflow to make other things possible. So what is a cluster? A cluster is basically a group of another definition. So basically, I've made these definitions to do these specific things and then just put them in a cluster to make one tool to do it. And so if you hover over one of the components, you're going to see that there's a cluster inside. And if you double click on it, you see inside, this is the definition that makes up that cluster. So then you can take it if it's not working the way you want, or if you want it to do something else, you can figure out how it works by looking at the cluster inside the cluster, and you can change it. And maybe if you make something useful, you decide to put it on GitHub and share it with everyone else. So on GitHub, I have all the source files. I have a README. I have all the icons as an Illustrator file, the documentation. So basically, if you want to contribute, this is where you go to put the files. And then we also have a forum. And this is where you can start discussions, ask questions, anything like that. And I'll also be updating if I'm doing more webinars, anything like that, I'll put it here. So go ahead and sign up on this, and you'll get notifications if I add anything. What Crystalon is not, it's not an all-in-one tool. It's modular, so it's made to work together with other plugins. You don't need to have these plugins, but it will make your life a lot easier to use a lot of other things. So basically, I wasn't trying to reinvent the wheel by making this. So for instance, things like meshing for 3D printing, there's already really good software out there for doing that. So there's other plugins you can use, and I'm not going to try to make them myself. So one of these tools, Kangaroo, which does live physics, which is really helpful for things like working with meshes. Weaverbird, also a mesh editor, super helpful. I highly recommend getting this. And Dendro I use all the time for making meshes. This is volumetric modeling, so it makes things a lot easier in doing Boolean operations and everything like that. And I'll be showing how to use this later. And Millipede for FEA, simulation and optimization. Like, I'm not an engineer. I don't get paid to do simulations, so I don't buy the other tools. Like Karamba is a very great tool, but I don't necessarily need something like that, but Millipede is very good and it's easy to use. And so I tend to use Millipede. So let's talk about what is a lattice structure. So in crystallography, this is where this term lattice structure kind of comes from, is the arrangement of atoms in a crystalline material. And so the smallest group of atoms is called the unit cell, and that's what you see here. So for different materials, you see these unit cells have different structures, and this is the base of the symmetry of the crystal structure. And so each of these cells, unit cells, gets repeated in 3 dimensions, and that's what makes up your lattice. What makes a diamond so hard? It's because of the structure. So in every crystal and lattice material, the structure of the lattice is what gives the material its physical properties like strength, density, even optical properties. And it's the arrangement of atoms and the bonds between them where they're sharing electrons that give the materials their strength. So why do we use lattice structures? So most people just think of structural lightweighting. This is the most obvious application. You reduce material and mass while maintaining the desired strengths. And basically, obviously, most man-made things can be made with less material. And this is just a way of doing that in a simple way. But there's a lot more things you do with lattice structures. Things like structures for bone tissue attached to in medical implants. Things like using flexible materials to absorb energy, kind of like engineered foams and padding. Structures with high surface area that create turbulence in fluids for heat exchange, and materials with a specific porosity that we can use for filtration. And even plastic. Plastic is a great insulator, and especially if you trap air in those pockets, it makes a great thermal insulator. So how do we make a lattice structure? So you can use Crystallon, and if you want to use Crystallon, you can continue listening. So we can't 3D print atoms and tell them that they need to share electrons, so we can't really make crystals, but we can make things that simulate that kind of thing. And we simulate those bonds between the nodes with things like beams or surfaces made of a material. And so I use the terms beam and shells because that's what's used in FEA. Shells are kind of surfaces, beams are thin, either rectangular or cylindrical tubes. A voxel is a unit of space that a single unit cell fits inside. And so we create voxels inside of our geometry to populate with a lattice structure. And then last, we can add some skins or some kind of other mating surfaces, critical geometry, and then we'll add that to the lattice. So what are the steps? So this is kind of the basic workflow, and this is going to be pretty similar for any kind of lattice software you're going to use. You're going to start with a design space. This is your part. This is your thing you want to make. And we fill that space with voxels. And how we fill that space is what's going to make different softwares different. Once we have these voxels, we'll decide, we'll pick a unit cell, what we want to fill those voxels with, and we populate those voxels. And then usually there's going to be some trimming, cleaning, modifying we want to do to that lattice because, you know, there's going to be beams that go places you don't want them to go. You're going to trim it to your design space, the desired shape you want it to be, things like that. And once you have your final lattice, then you're going to do, usually you're going to do some kind of simulation or optimization. And that's typically where you're going to go back to step 2 or 3 and change the design until the simulation, until the lattice does what you want. And the last thing you do is make a mesh. You don't need to make a mesh every time just to see it. And that's what's nice about using Grasshopper and Crystallon is you can parametrically make this, and in the end, then you just make a mesh. So what is the benefit of Crystallon? Well, most software out there is, it's kind of an external tool. And so basically you have to like design a part in Rhino or SolidWorks or whatever, export that and bring it into this other software. And then you just have this kind of dumb geometry, this shape that you want to fill with a lattice. But with Crystallon, we're inside of Rhino and we can use Grasshopper to create our lattice design parametrically. So before we dive in, let's kind of look at what resources available. So when you download Crystallon from foodforrhino.com, you get things like installation instructions. You get documentation. You get libraries, which are the source files, and you get example files. So in the documentation, it's 75 whole pages I made all by myself. There's a description of every single tool, every component, what it is, the icon, the name, description, description of every input, what kind of data it's looking for, and what it's going to do, and the outputs. And so if you're ever wondering what a tool does, you need an example, check out the documentation. We also have example files. So I've made an example file for pretty much every single tool. So if you're trying to understand how a tool works, check out the documentation and check out the example files. And so the Crystalon toolbar is basically laid out kind of step by step of the workflow you will use. We'll start by making voxels. We'll populate those voxels. We'll do some modifications. We'll do some things to thicken them. The 2D tools are kind of experimental for right now. They're kind of used for making flexible materials out of 2D materials like laser cut lattice hinges or working with flexible sheet materials. I won't talk about those during this, but it's something, if you're interested, you can check out. And lastly, the utilities are mostly for import and export to FEA kind of applications. So I'll be working on more file formats as I go along, but for right now I have like INP files, which are for FEA. So if you're using ANSYS or Nastran, sorry, if you're using ANSYS or Nastran, you can use these input files and do some simulation. There's also import and export for in topology, the LTCX format, and I'll be working on some more. Cool icons. What do they mean? So I'm not really a graphic designer, but I tried my best at making some icons that kind of describe what these tools do. So each tool will kind of have these icons, and the blue parts on top you'll see kind of tell what that function is going to do. So the ones with the X mean it'll work with an absolute value and absolute distance. The ones with a little sine wave means it works with a parameter, which is kind of divisions of a distance. Things with a little point means it uses points and values. And things with a line means it'll work with attractors, and attractors can be curves, points, surfaces, anything. All right, you guys ready? All right, wait. First, I'm going to talk a little bit more about design space, design approach. What are you designing? What should your approach be? When does this come into the process? So a lot of times I get questions like this. Can you lightweight this, please? And basically the answer is no, sorry. I mean, this part was obviously designed for injection molding. And if we want to make it lighter, I wouldn't even know where to start. And so if we want to design for additive manufacturing, we kind of need a whole new mindset. We need to start over and think about what does it do? What are the critical features? What's the entire space I can use? So I like to compare this to topology optimization. So if you guys don't know what that is, topology optimization, it's basically an algorithm for distributing material with the least amount of mass and the maximum stiffness. So make the strongest, lightest part possible, or it'll try to. But if you give the algorithm a limited design space, so if you design the part basically completely and then ask it to take material away from that, there's not much you can really do. But if you give it all the space it has to possibly work with, then it can come up with a solution. And so you can see here, like the first design, the engineer was pretty close to what would be optimal, but the design, the topology optimization did things a little bit differently, a little better probably, who knows. And let's talk about design approach. So like I said, most software, you're going to be very limited because you have to import like this, what we call dumb geometry. You just export an STL or a step file or an IGES file into this program, and you lose all that information about the design, the surfaces it was made that were used to build it, the curves you used to build it. And so you're limited to just a volume that you fill. And so sometimes for a lot of applications, that can be totally fine. But if you want to do more, That's probably why you're here. So what is a good design approach? So lattice structures are most effective when aligned with the direction of stress. So ideally you want to have your lattice, you want to make your lattice conformal to the surfaces or the stresses that are going to be applied on it. And so a good example is if you look at bones, bones are constantly deconstructing and rebuilding themselves based on the stresses. And then those stresses are what it senses basically through chemical, electronic pulses. When you put weight on your bones, it tells it to build bone mass in certain areas. And this is also why astronauts lose bone mass over time. It's because they don't have gravity to apply stress to their bones. So how do we use Rhino geometry to make our lattice structures more conformal? So like the example, like B is basically what we're going to be able to do. C would be nice in the future. We're getting there. And D is probably what you're going to see in most software. But with Rhino, we have these volumes. We can use surfaces. We can use curves and points. But then also with Grasshopper, now we have things that we can use like physics. We can use data from FEA simulations, all kinds of tools that we can take data and within the process of designing the lattice, use that data to help design the lattice better. So what kind of structure should you use? Well, I don't really know. So it really depends on what you're making. The best structure is completely up to your design, your application. One unit cell might work great for one design, not for another. So it's always trial and error. There's no lattice design software that's just going to give you a solution for what you want to do. It takes testing, it takes simulation. A lot of the times it takes actually printing the thing and physically testing it because it can be really hard to simulate as well. And it also depends on the process and material. So before you're ever designing anything, you should really know how it's going to be made and what material. So each process has its own advantages, its own limitations, things like material thickness, if it needs support material. And those are all things you should take into account as you're designing your lattice structure, thinking about how it will be built and what material. All right, so I went through that fairly fast, so I think we've got plenty of time to do some demos. So let me hop over to Rhino and we'll get started on that. All right, so I'm going to start first with showing kind of the voxelization tools. Let's start with just creating some voxels on some things. If your geometry is kind of a strange shape, like you have this